Hi class, my name is Sarah Wilkins. This is the presentation for the Advanced Group Concepts for week 6. Aspirin was one of the first drugs to ever be produced. In the late 1890s, aspirin was discovered by a man named Felix Hoffmann, and he was at Bayer in Germany. It wasn't until much later that we discovered the mechanism by how aspirin works, but today there is a huge wealth of information that is available about how exactly aspirin inhibitors the cyclomonooxygenase, or COX. For this assignment, we're going to investigate how aspirin works, both looking at the pathway levels as well as a mechanistic level, or the mechanisms. So we're going to look a little bit more into how aspirin works, both on a pathway level and a mechanism level. I'm going to walk you guys through the pathway and we'll go into a little bit more detail about the structures, metabolite names, enzymes, cofactors that essentially aspirin does inhibit. And we're going to look at that mechanism as well. Alright, if you guys can see here, we have figure 2, which is the different classes of fatty acids. And this is going to be very important when we're looking at the different components of the mechanism that we'll be looking at. So we have the arachidonic acid. So if you look over by the omega-6 fatty acids and kind of go down the line there, you can see the AA down there at the bottom. So the omega-6 and the omega-3s comprise the two classes of essential fatty acids. The present compounds of each class, the LA and the linolenic acid, so the LA and the ALA, give rise to the longer chain that derives inside the body. Due to low efficiency of conversion of ALA and the long chain omega-3, the EPA and the DHA, it's recommended that the EPA and DHA are essentially gotten from additional sources, so dietary sources. A really important part that we have to look at and keep mind of are the prostaglandins, and in this process we are looking at prostaglandin E1, which is alprostadil, and this prostaglandin is going to work against E2, which is the second prostaglandin, and it does so by acting as a vasodilator. Additionally, it's going to block the toll-like receptor on the cell that's going to prevent entry of any of that E2. Then we have prostaglandin E2, which is dinoprostone, and that sends a message of inflammation to the nucleus of the cell. However, this can be bad when it's constant, like when it's constantly happening or there's too much of it, because it can turn the growth genes on, and this can cause cancer with all that extra growth there. This also may suppress T-cell receptor signaling, so keep that in mind. Then we have prostaglandin E3, so we have that COX component there. So the cyclooxygenase metabolism, that can travel into the cell's nucleus directly, and it can also promote stability of the cell. Next we have the arachidonic acid, the AA, which we talked about a little bit before. This acid is an unsaturated omega-6 fatty acid. This can be found in the cell plasma membrane where it is bound to the phospholipids. This is not involved in PGE2 production, which contributes to inflammation. And AA does also undergoes metabolism by the COX enzyme, which is referred to as that cycloogenase enzyme. So we want to look a little bit at like what does aspirin do? What is aspirin? Essentially, aspirin is a channel blocker. This is going to happen during metabolism, and it prevents prostaglandin synthesis of PGEs, which in return will reduce inflammation by reducing that inflammatory response. Aspirin donates acetyl group to the serine residue that will lay on the path to the active site, which will block that channel. And this is what is called that COX inhibitor that we talked about. And lastly, I just wanted to show you guys this. We can see the COX pathways for NSAIDs, for aspirin, and kind of what plays a role in all of those and how that's kind of broken down. So I hope that gives you guys a better explanation, an idea of kind of how those mechanisms all work together and those components and structures as well.